Okay, welcome to E674 Modern Power Systems. In the last class and in the last video, we have discussed the control of active power and the frequency. So today we will talk about the control of voltage and reactive power. Okay. So let's consider a simple circuit, right? So you have a voltage source and then impedance, let's say R plus JX, and then will be a power flow in here, so P plus JQ. Let's say the current going out from here is I, right? And let's say the if you have a load connected, then there will be a current I flowing in here. So this is the load, right? And let's say the terminal voltage is V, right? So we can write the equation. Actually, E is equals to V plus I times R plus JX, right? And the corresponding phasor diagram, if you draw that, you will get something like this. So I'm not going to go in detail, you know how to draw it. If this is the current I, okay, we take another color. So this is the current I, and if this is the voltage V, and V plus I times R plus JX, and it's the 90-degree from here. So this, let's say this is I times X. So we'll give you the voltage E. It has to be straight, but okay, it's fine. Okay, okay, so the actually the I can be divided into two parts. It's a real part and the reactive part. So let's call the real part is IP and the reactive part is IQ, right? IP and IQ. Okay. So you can do a small maths right here, and you can come up with the set of equations. So let's do something like this. So let's say this is point A, right? And then this point is, let's say this is point B, right? And so from here to here, actually let's call it the delta V, right? So you can see that this delta V consists of couple of parts. That is, from here to here you have one, right? So let's say this is B, and then from here to here you have another one. Let's call this is point C. So AB plus BC will give you the delta V, right? And similarly you have other locations here. Let's call it G, and then this, let's call it delta V, right? So with the help of delta V and this simple delta V, I can write the Pythagoras law. E squared is equals to V plus delta V squared, right, plus delta V squared, right. So now with the help of all the parts that I have marked here, you can write the capital delta V as here you have this angle is, let's say, perfect angle 5, so this angle would be the same as 5, right. And then this is 90, so this would be 90 minus 5, so 90 minus 5, so this is 90, so this will become, this angle will become 5, and so on, right. So with the help of that, now you can write the this AB is equals to I times R cos phi, IR cos phi, plus here again so you have Ix sine phi, that is this part from here to here, right. So Ix sine phi, right. So this is become 5, so this is also equals to 5, so you have IR sine phi, right. Right, so squared plus then the simple delta V squared, I can write it as so with the distance dg becomes I xi cos phi, right. So Ix cos phi, and then the minus this distance, which is IR sine phi square, right. So some simple geometry, and now I can manipulate this equation a little bit by doing this. So you have V plus, let's say, R over V times I, right. So cos phi plus X over V times I sine phi squared plus same arrangement, X over V I cos phi plus R over V I sine phi square, right. So then this would be equals to V plus we have a R, Vi cos phi is the active power P divided by V plus Vi sine phi is the reactive power, so x cube over V squared plus again Vi cos phi is the active power plus the Vi sine phi is the reactive power, right. So this is the now if you can remember, this is the capital delta V terms, and this is the simple delta V term, right. So you can write, say that the capital delta V is equals to Rp plus xq over V, and simple delta V is equals to xp plus Rq over V, right. Now for a typical transmission systems and for the networks where x is much greater than R, okay, so when the x is much greater than R, this part will dominate. So you can see that the capital delta V is proportional to the reactive power, and then for in the x greater than r, for simple delta v, this part will dominate, so delta v is proportional to the active power, simple delta v. Okay, so you can see that the right, okay, so let's keep it there and then move on, and then we will eventually relate this to the voltage and the frequency, right? So let's apply the same concept for the two generator system. Okay, so let's consider the two generator power system. Like you have bus A and bus B. So the generator 1 GA is connected to bus A and GB is connected to bus B, and let's say you have each bus, you have the load LA and LB, right? And then you have the transmission line. Basically the reactive power is dominating, so Jx, right? So you have generator station A and generator station B. So if the machine at A is in phase advance of the machine at B, right, and the voltage at the VA is greater than VB, right, then the you know that the P and Q flow from A to B, right? Okay. Okay. So then by changing the generator excitation, we can change the VA and VB, and if we make that VB is greater than VA, you know that we can reverse the power flow, right? So you can see that the active power can be transmitted from A to B or B to A by changing the fuel supply to the turbine, whatever the fuel is, either it is coal or either it is the water or whatever, right? So changing the fuel supply or changing the excitation, we can change the power flow, right? So that is talking about the active power, right? But the reactive power can be controlled by changing the voltage magnitude, right? So you can control the reactive power can be changed by controlling the voltage. Actually this has to be interchange. The reactive power can be controlled. That's what we are going to control by changing the voltage magnitude, right? So you have seen that if the x is greater than the r, so these two operations, the active power control and the reactive power control, can be implemented independently, right? So I will write that part as well to make it complete. active power can be controlled by changing the fuel supply to the turbine. Okay, and then when X is greater than R, the P control, that means the active power control and the reactive power control, are independent. So we can do it independently, right? But you can see, like, if you look at the equation, that is not that straightforward here. So they both have the active power and reactive power, but when the X is greater than R, the one dominate the other. So we can see that one can be controlled independently of the other, right? Okay, so typically the reactive power flows to the node of lower voltage. So the reactive power will flow to the lower voltage node, right? And then if there is a deficiency of the reactive power at a certain point, so it has to be supplied from the connecting lines, and because of that the voltage at the point will fall, right? If there is a of reactive power at a point, okay. So this has to be supplied from the connecting lines. That means the reactive power should come into that particular point. So because of that, the voltage at the point will fall. Okay. And if there's a surplus of the reactive power, the voltage at that particular point will rise. Okay, that means the reactive power is generated at that point. Okay, so when the Q is equal to 0, right, then the voltage drop across the line is 0, right? So if you have two line, if you have a line with the voltage V1 and V2, right, if this is lower, the reactive power will go in this way, and if this is higher, the reactive power will go in this way, and if this difference is 0, there will be no reactive power, right, if they are equal. Okay. So then so there will be, when the Q is equal to 0, you can see voltage drop equals to 0. That means delta V, this is the voltage drop given by this equation according to our previous derivation, right? And from this I can write the Q is equals to V dot delta V minus R times P over X, right? So if we assume that the V1 is constant, okay. And when then we will try to so we assume that this one is constant, and we will see the effect of keeping the v2 constant as well, okay. So assume v1 is constant and consider the effect of keeping v2 constant, that is basically delta v, the change, is equals to constant, right? So you can write the q2 from this previous equation as v2 delta v minus rp2 over x, right? So this is equal to v2 delta v over x minus rp2 over x. So we keep the v1 constant, and we consider the effect of keeping the v2 constant, so which eventually take the delta v constant, and x is also a constant, so you can see this part will become a constant, and you have this rp2 over x, right? Because this whole thing is a constant now. Right? Right? So so if this the q2 is not there naturally in the circuit, right, then you have to obtain it from the other way, otherwise from somewhere, right? So the q2, right, if not naturally available, we have to obtain it through connecting inductor or capacitor, depending on whether we need to produce reactive power or absorb reactive power, right? Capacitor at point B to get this the reactive power requirement, right? Right. So now let's consider what happen if the active power changes from P2 to P2 dash, right? If active power changes from P2 to P2 dash, right, and V2 remain constant, okay, then the new Q2 dash would be K minus R over X P2 dash, right? And the change in the reactive power Q2 dash minus Q2 is equals to R over X P2 dash minus P2, right? So you can see that the increase in the active power also cause an increase in the reactive power, right? But since the R over X is very small, this change is very small, right? So from this equation, what you can interpret is that change, okay, let me say increase in the P active power increases the reactive power, right? But since the R over X is very small, because X is much greater than R, this change is very small. Okay, so let's see this relation between the voltage, power, and reactive power at a particular node in much more detail, right? Sorry. What to say is the relation between voltage, power, and this is active power actually, and reactive power at a node. Okay, so let's try to see, right? So we have seen that the voltage, the phase voltage at a node is a function of P and Q at the node, right? And the voltage at the node also depend on the voltage of the adjacent nodes as well, right? So we can write an equation for the voltage at particular node is a function of the active power and the reactive power, right? uh, and if we get the total difference of the uh, this voltage, we can write it as delta V over delta P dP plus delta Q over delta V over delta Q times dq, right? So if I rearrange this a little bit, I can get that delta V over delta P times delta P over delta V dP divided by delta P over delta V, right? Plus I'm just rearranging, multiplying by delta P over delta V and dividing by the same. So here delta V over delta Q times delta Q over delta V dq over delta Q over delta V, right? So you know that this part is 1 and this part is 1, so dV is equals to dP over delta P over delta V plus dq over delta Q over delta V, right? So you can see that the change in the voltage V, right, in the voltage at a node is defined by two quantities. That is delta P over delta V, and the other one is delta Q over delta V, right? So let's consider our two bus system. Yeah, I will do it in the other side so I can continue my discussion. So for two bus system, we have V1 and R plus JX Here you have V2, this is bus 1, this is bus 2, right? So for the 2 bus system, we can write that the V1 minus V2, okay, is equals to Rp plus XQ over V, right? So the not V2, let's say V, right? So this is the actually the sending end voltage, right? So, and this will be a constant. So let's say this is the generator bus or something, so we keep the voltage constant, and let's say this is just V, which is the receiving end voltage, and this depend on P and Q, right? So you can see that, right? So so this equation we can get from this equation, we can say V1 minus V times V is equals to Rp plus XQ, right? And taking our dabba P and over dabba V and dabba Q over dabba V, so the dabba P over dabba V will give me V1 minus 2V over R, right? And then the dabba Q over dabba V will give me V1 minus 2V over X, right? So then I can write the total voltage deviation, dV is equals to dP over dabba P over dabba Q plus dQ over dabba Q over dabba V, right? So this will give me dP times R plus dQ times X over V1 minus 2V, right? And for constant V and delta V, right? Right, that means there's no change. So then the dP times R plus dQ times X should be 0, and then you get the relationship between the changes in the reactive power and the change in the active power as this R over X. So you can see the very similar equation, right? So it is depending on minus R over X times dP, right? Right. So you can see that the right. So from this discussion we can conclude that the smaller the reactance, right, associated with the node, then the larger the dabba Q over dabba V would be larger for a given voltage drop. Okay. greater the number of lines meeting at the node, okay, the smaller the reactance x, right? So which gives the same scenario here. So larger the daba q over daba v. Okay, so you can see that the daba q over daba v depends on the network configuration, right? And the greater the daba q over daba v, it's more expensive to maintain the voltage level by injection of the reactive power, right? So greater the daba q over daba v, more expensive to maintain the reactive power or maintain the voltage level by injection of q, reactive power. Okay, okay. So if we calculate the short circuit current, okay, uh, at the receiving end, because we are looking at the reactive power at the receiving end. So if we calculate the short circuit current, that would be V1 over X, right? Which is because R is much smaller than X, right? And then at no load, V is equals to V1, right? So you get the daba q over daba v is equals to minus V1 over X, which is equals to minus I short circuit. So that is the magnitude of the daba q over daba v is equals to the short circuit current, and this sign is basically say the nature of the reactive power. Okay? The sign gives the whether it is a capacitive or inductive reactive power that is flowing, right? So you can see there's a relation between the short circuit current and the magnitude of the reactive power. Okay. So in a normal operation, V is within few percentage of the V1, and because of that the daba V over daba Q at V is equals to V1 gives the useful information, because in the normal operation we will slightly vary around V1 information, right? So by calculating this, you can get an idea about the reactive power and the voltage characteristic, for a small variation from the nominal voltage, right? So in order to get an idea about the behavior of the reactive power and the voltage, further we will look at the reactive power characteristic of different power system components. Power system components, right? So we will start with the synchronous generator. Right. So the synchronous generator can absorb or generate reactive power. Reactive power. Okay. So this can be basically controlled by controlling of the field voltage. Okay. So by controlling the excitation, you can control the reactive power absorption or generation. Okay. So the how much the reactive power can be supplied or absorbed is given by the reactive power capability curve, right? The amount of Q absorbed or generated is given by the reactive power capability curve of the synchronous machine for the synchronous generator, right? To be more precise, the overexcited machine will generate reactive power. Machine generate reactive power, and the underexcited machine will absorb the reactive power, right? So that is how the synchronous machines have the acting. So we will later see that we can use the synchronous machine, or what we call the synchronous condensers, in order to control the reactive power and the voltage in the system, right? Next we will look at the overhead lines. Right. So this can also absorb or supply reactive power. Okay, and that is basically based on the loading condition. Okay. The line draws reactive power if loading is higher than the what we call the surge impedance loading. Okay, and it supplies the reactive power otherwise, right? Q otherwise, right? So what is this the surge impedance loading, right? Just a note. Impedance loading, or called SIL, okay, of a transmission line, right, is the megawatt loading of a, I would say, transmission line at which natural reactive power balance occur. Okay, so that is in the line, you know, you have the capacitors and the inductance, right? So then at the surge impedance loading, right, the capacitive VAR of the line will be equals to the inductive VAR of the line, right? So that means V squared over XC would be equals to I squared XL. So this will give V over I is equals to square root of XL times XC. So this is where the resonance occurs actually, 25FL times L over 25FC over L, where the L and C are the impedance per inductance per unit length and the capacitance per unit length. So the V over I would be equals to L over C squared, which is equals to the characteristic impedance, right? So this is called the inductance per unit length, and this is the capacitance per unit length, right? Right. So this is how the line will behave, right? So it can either absorb or generate the reactive power. So the other component that we are interested is in the transformers, right? So the transformers basically absorb the reactive power. Okay, and if the transformer the reactance is xt in per unit, right, we can calculate the ohmic reactance is equals to V times xt over rated current of the transformer, right? So and then we can calculate the reactive power absorbed or the VAR absorbed is equals to 3 I squared V xt over I rated, which is equals to 3 I squared V squared over IV rated times xt, right? So this is the rated in VA. So you have V here, the VA base is there, so you have, sorry, VA of the load squared divided by the rated VA times xt, right? So this is how you calculate the reactive power absorbed by the transformer, right? And if you look at the cables, the underground cables, right, they are actually the generators of reactive power. This is basically due to high shunt capacitance in the cables, right? Like for example, 275 kV 240 MVA cable produce like 6.25 to 7.5 MVAR, right? And 132 kV cable will produce about 1.9 MVAR per kilometer, right? 33 kV cable will produce about 0.125 MVAR per kilometer, right? Okay, and then the loads, you know, the mostly the loads are reactive, right? And so most of the loads are, especially in the industry, they are reactive. These machines and so on, the motors, so they are the reactive. Even in the homes, you have these fans and refrigerators and so on. So they draws the reactive power, right?